Today's video is on isotopes, which will cover a part of Chapter 2 as well as 3.2 in Chapter 3. In this video, we are going to look at what an isotope is, how to determine the mass of each isotope in the average atomic mass unit, and the percentage of each isotope when we're looking at the meaning of abundance of each isotope, or a percentage. So what is an isotope? If you recall, the atom has three main parts: protons, neutrons, and electrons. In the nucleus are the protons and the neutrons. The two of these make up the mass of the atom, while the electrons and the energy levels makes up the space of the atom. The proton has a positive charge, and every atom of an element will have the same number of protons. This is what determines which element we are looking at. The neutron has no charge, and each element has two or more stable isotopes based on the number of neutrons. So in your chemistry book, you will notice superscripts and subscript numbers before the symbol. On this page, you notice I have an Na at the bottom. If I write, and let's see if I can get my pen to work, if I write the number 23 at the top, a superscript, that is the atomic mass for that element. So that's telling us what's the mass for that element for each one we're looking at. At the bottom, if I make the subscript, that's looking at the atomic number, the number of protons. So here I would be looking at sodium, and it would have the number of neutrons would be 12, because 23 minus 11 would give us the number of neutrons. Sodium actually has more than 5 isotopes. Most have a half-life of less than a minute. 2 of them have an isotope of at least a year or longer. So if I have sodium, again, Na for the symbol, and if I have the atomic mass of 24, the atomic number, the number of protons, would still be 11. That would tell me that the number of neutrons is 23. 24 minus 11. Now, average atomic mass is based on the percentage of each isotope for that atom. So here on this screen I have 3 types of carbon: carbon 12, carbon 13, and carbon 14. Carbon 14 is radioactive and is used in carbon dating, but it's negligible when we look at the numbers or percentages for how much carbon 14 is there. When you look at the 2 basic isotopes, you have the primary one, carbon 12, where almost 99% of carbon atoms, if we looked at 100 carbon atoms, would be made up of carbon 12. Carbon 13 is 1.11%. So that means the majority of the carbon will have 6 neutrons, and a very small amount will have 7 neutrons. On slide 4 here, we're going to take and look at having 100 atoms of any element and see if we can determine the numbers of isotopes. No single atom contains the exact mass for an atom. Everything is an average atomic mass, what's also known as the atomic weight. So let's see if we can determine the abundance of any one isotope. Using the percentage for the isotopes of carbon, we can determine the atomic mass unit for each of the isotopes. We need to set up our basic problem. We're going to use a formula where you take the percentage and you convert it to a decimal, multiply it by the mass of the isotope, and then add the masses of each isotope together to get the average atomic mass for that element, or what is known as an AMU. You notice that is what I've done here. I've taken carbon 12 and carbon 13, converted their percentages to a decimal, and then multiplied them by the atomic mass for each of those isotopes. You add those together and you get 12.01 AMUs. Here I have the breakdown of copper. And let's see if we can determine for copper what's the abundance and the atomic mass for each of the isotopes. Carbon 63, the atomic mass is 62.93, and there's 69.09%. Copper 65 is the atomic mass of 64.93, and the abundance is 30.91. So we'll do the same thing. We convert the percentage, multiply into a decimal form, and multiply it by the atomic mass, and you end up with sig figs to be 63.55. When we look at the atomic mass, it's 63.55 AMUs if you're doing atomic mass units, or grams if you're doing atomic weight. Here are some practice problems using different percentages for each of the copper isotopes. See if you can figure out these 5 problems. If you have questions, come see me before school or after school. All right, but what if we know the atomic mass and we want to know the percentage of each one? That's called the abundance. Lithium has 2 isotopes, lithium-6 and lithium-7. There is a basic formula. First thing you need to do is figure out what's going to be X. You can use algebra for this. You use the lighter isotope as X, and then your heavier isotope is going to be 1 minus X. So why do we use the number 1? Well, remember that we're changing our percentage to a decimal, and 100% divided by 100 equals 1. So you take and multiply your mass by each of the things, so 6 times x gives you 6x, plus 1 minus x times 7 means you get 7 minus 7x. Take your x's, combine them together, you get a negative 1x plus 7. X is going to equal 0.059. So you multiply that by 100. Lithium-6 is 5.9%. Lithium-7 is 94.1%. Add those together, you're going to get 100%. That way you know you did it right. Okay, so let's do another problem with boron. Boron also has 2 isotopes, boron-10 and boron-11. Here's the basic formula again. Take your mass times the x, and then take 1 minus x multiplied by the mass of the second isotope. See if you can figure it out. Did you get the same answer as I did? If you have questions, bring them to class.